Suppose that the minute hand of a clock is 15 millimeters long and the hour hand is 12 millimeters. How fast is the distance between the hour hand and the minute hand changing at 1 p.m.? So what the question is asking for is to find the rate of change of side C, which is the distance between the hour hand and the minute hand. To do this, we can draw a triangle. And then using the law of cosines, we can determine side C and the angle between the hour hand and the minute hand. So the law of cosines is C squared equals A squared plus B squared minus 2AB cosine C. So we are going to plug in numbers for A and B. We have our minute hand, which is 15 millimeters long, and our hour hand, which is 12 millimeters long. The next step to take is to find the derivative of this equation. We end up with 2c, derivative of c, equals 0 plus 0 plus 360 sine of angle c. Then we solve for dc over dt, which is equal to 180 sine of the angle of c over the side of c. We are asked to find this rate of change at 1 o'clock. So now we're going to draw a clock, and we can see where everything is. So there's the minute hand, there's the hour hand. So the total degrees in a circle is 360 degrees, and we are trying to find what that angle C is, and we're dividing this by 12 because an hour is a 12th of the clock, which is equal to 30 degrees. So now we know that our angle C is 30 degrees, and we are still looking for what side C is in order to find the rate of change of it. Our next step is to plug in the angle C, which is 30 degrees, in order to find what side C is. So we get our c squared, which is 67.23, and in order to find the c, we have to find the square root of that, which is going to be 7.565. And now we are looking for our rate of change of c. So we are drawing our clock again so that we can see where everything is. Got our minute hand and our hour hand. Our minute hand is going to be A, and our hour hand is going to be B. So we need to find the rate of change of the angle right now. And so in order to do that, we're going to do rate of change of A minus rate of change of B. And I don't know if you can see that, but yes, Josh just wrote that my eyes were closed when I was filming this because I was kind of falling asleep. It was 2 in the morning. So we have our rate of change of C, which is what we're looking for, the angle right now. So we're just rewriting this equation for everyone. Okay, so to find the rate of change for A, the minute hand, speed of the minute hand, going to look for that, and then we're looking for our rate of change of the hour hand also, to plug this into the equation. Despite where the arrow is pointing to, this is actually the speed of the hour hand, which is 2 pi over 12 times 60, which equals 2 pi over 720, which is also equivalent to pi over 360. Okay, the next one. So I guess Josh is changing the hour and the minute thing so no one's confused. We're going to find the speed of the minute hand now, which is 2 pi over 60, which equals pi over 30. Now we plug these two numbers in to find the rate of change for the angle. So now we're going to use what we found to plug in back into the equation to find the rate of change of side C, which is 180 sine of the angle over c times the rate of change for the angle. So we've got our angle of 30 degrees, which we're going to plug in for little c. And then we've got our big C, which is the actual side length, and that is going to be what we found earlier, which is 7.565. We're going to multiply this by the 11 pi over 360, and we get our answer of 1.142 radians per minute. And there you go.